Thus far during these lessons on the fundamentals of oscilloscopes, we have only used the scope's default acquisition mode, which is called normal. Personally, I think these scopes have too many normal modes. There's normal trigger mode, normal time mode, and now normal acquisition mode. Some scopes call it sample mode, which may be more descriptive. This acquisition mode, which is what you'll be using most of the time, simply means the scope takes consecutive samples of the incoming signal, one after the next, evenly spaced based on the sample rate. And then after filling up the acquisition memory, which for this oscilloscope is 2 million points, the scope plots those points onto the scope's display without any kind of manipulation or digital filtering of the digitized data. You can think of these 200,000 points, which forms a volts versus time waveform, as a complete picture of the input signal. Hi, my name is Johnny Hancock, Product Manager for Keysight's Infinivision oscilloscopes. In this lesson, we are going to look at some examples where you might want to use some of the oscilloscope's special acquisition and display modes. Let's start with an example to show where the normal acquisition mode fails to show us what's really happening on our input signal. Here's a 30 Hertz sine wave, so it's fairly slow, and it's got what appears to be intermittent glitches popping up and down. So you might think this is a problem signal. But are they really intermittent? Let's zoom in and take a closer look at, say, that glitch that's right at center screen. So now I'm at 100 nanoseconds per division. I can see that it's not intermittent. It's not jumping up and down. It's very stable. And if we were to measure the width of this glitch or pulse, it says it's about 38 nanoseconds wide. So why was it jumping up and down when I was looking at the big picture versus now it's very stable? Notice right now I'm sampling at 2 gigasamples per second, which is more than fast enough to capture this relatively narrow pulse. But as I open up the horizontal to capture a longer and longer time span, you can see that the sample rate begins to decrease when I capture longer time spans. And when I go back to where it was before, capturing 3 cycles, 10 milliseconds per division, so I'm capturing 100 milliseconds of time. Now it's only sampling at 10 megasamples per second. All scopes will reduce their sample rate when you set the horizontal to capture longer and longer times because of limited memory. Now this scope has a fairly good amount of memory, 2 million points, but at some point when you divide up 100 milliseconds across screen, that's telling the scope, okay, you're going to have to sample slower in order to capture this amount of time span. So how can we fix this issue? Let's see what acquisition modes we have. So I'll go in up here at the horizontal, acquire, AC mode or acquisition mode. Right now we're in the normal acquisition mode, which means sequential samples. There's a special acquisition mode called peak detect. And once I go into the peak detect mode, now you can see those glitches or narrow pulses it's capturing is very stable. So now we're capturing the big picture and the fine detail. We're seeing the forest and the trees at the same time. But notice, and let me explain what's happening here. We didn't increase the memory. What happens is the scope is capturing groups of samples and picking out the positive peak and a negative peak for a group and throwing out all the others. And so it's storing 2 samples for every group. Then it goes down to the next group, stores the min and max, then the next group. It's a little complicated, but it works. The trade-off though, if I press stop and zoom in, you can see that I have very little detail. I actually just captured one point up here, one point over here. We don't have a lot of detail. So let's take a look at another example of a different signal where another acquisition mode might help us. This is a 1 kilohertz sine wave, and as you can see, it's got quite a bit of noise riding on it. This is one of the built-in education training signals of this oscilloscope. But what if you don't care about the noise? It's random noise. You can use, again, let's go into the acquire menu. You can use the averaging mode to average out that noise. And then you can also, right now it's selected for 8 averages. I can increase it, I believe, all the way up to 64,000 averages. Right now, I got 64. And now you can see you have very high resolution measurements. So we've essentially averaged out the random noise. The only requirement for this particular acquisition mode is the input signal must be repetitive. You can't average something that is not repetitive. So what about single shot events? What if I want to eliminate noise on something that's single shot? How do we do that? I've got the scope set up now to capture a single shot event. The event, single shot, is actually one of our built-in training signals. And so I'm going to capture it one time. And there you can see, if you look close, there's a little bit of noise riding on the signal. And if I want to get rid of that noise, I can't average it because it only happened once. But there's another mode called the high res mode. Let's go into the acquire menu and select high resolution. It erased the previous one. And let me go back into the menu where I can generate that single shot event again. Now you see with very high resolution. What's happening, it's running a filter. And it's taking groups of consecutive samples and averaging that group, and then moving over, averaging the next group and the next group. The trade-off is it gives you effectively lower sample rate and effectively lower bandwidth. But it does give you higher resolution. This scope has an 8-bit analog to digital converter in it. It can increase your vertical resolution up to 12 bits. Let's now look at a special display mode that can help reveal information. Here's a fairly high-speed digital signal. It's got lots of problems with it. You can see this falling edge here, it's jumping back and forth. We call that jitter. And there's some extremes out here that may be difficult to see. If I turn the waveform intensity up, you can see some popping out here. And over here is something similar we looked at earlier when we looked at some of the special trigger modes. There's a glitch happening here occasionally. Now, we have a special display mode called infinite persistence. Perhaps we want anything that happens randomly and infrequently, we want it to stay on screen rather than erase and bring up a new waveform. So I'm going to go into the display menu, which is located here on this oscilloscope, and select persistence. Persistence means how long something persists or stays on screen. And right now it's in the off position. I can select infinite persistent, which means it never erases. And here you can see various extremes that are painted in white now, different than the live waveform, which is in yellow. Maybe this glitch only happens once an hour, or the scope only captures it once an hour. The infinite persistent mode will leave it on screen. Now you can also go to variable persistence and tell the scope how long you want it to persist on screen. Right now, the time is set for 1 second. You can see things pop in there and then they fade and go away after a second. You could turn the time up to, say, 10 seconds if you wanted. I think this scope, you can go all the way up to 60 seconds, and then the next click is infinite persistence. Now, what if you want to view something that is really slow, almost mechanical? This is a half Hertz sine wave. If I change the horizontal so that I get a couple of cycles on screen, you can see it goes blank for a while, and then it starts tracing, and now it's not tracing anymore. If I press clear screen, it waits until it gets a trigger or it gets to center screen. There's a special, what we call time mode. You may have seen me go right past it when we were talking about Lissajous waveforms in the previous lesson. So let's go into the Acquire menu, and up here where it says time mode, normal, we showed XY for the Lissajous waveforms, and I just skipped right over the other selection, or I rolled right over it. It's called roll mode. In roll mode, the scope pretty much acts like an old strip chart recorder. Now, you may not be familiar with strip chart recorders, but if you think about lie detector tests, there's a piece of paper that's sliding along and the pen is just moving up and down, and the paper is basically the horizontal or time base. That's exactly how this is happening. This point over here on the far right, on a lie detector test, that's where the pen is down on the paper. It's plotting almost in real time the absolute voltage, and there you see history sliding to the left. And we call this roll mode. The scope is not triggering in roll mode. It's an untriggered mode. Some oscilloscopes will switch into roll mode automatically when you change the horizontal to capture a long time span. They just automatically switch into that if you're in the auto trigger mode. In our next lesson, we'll be talking about how to document your test results. This is probably something that your professors are going to require for your assigned lab experiments. Remember, to download additional information about the fundamentals of oscilloscopes, go to the URL listed on your screen. See you in lesson 17. Go Georgia Tech Yellow Jackets.